The universe whispered back, and we heard it. There are moments when the universe does not arrive with violence. No explosion tears the fabric of space. No shockwave ripples through the solar wind. No alarm sounds in the observatories scattered across our spinning world. Instead, it comes with something far more unnerving, a whisper in the mathematics, a deviation so small it could be mistaken for error, a shift so quiet that only those who spend their lives translating starlight into meaning would ever notice it at all. And yet, when they did notice, when the numbers refused to settle and the predictions began to crack like ice under invisible weight, something changed in the rooms where these calculations are made. Not panic. Not excitement. Something slower. Something that feels like the air before a storm that hasn't decided whether to break. Something passed us recently. Not close enough to see with naked eyes. Not bright enough to photograph from a backyard telescope. But close enough that our instruments could feel its presence, could track its motion against the fixed stars, could measure the way it bent spacetime as it moved. It was silent. It was ancient. It was impossibly, incomprehensibly far from home. And as it flew by Earth, as it traced that narrow arc through the space where our planet hangs in the dark, it changed. Not in a way that made headlines scream. Not in a way that lit up the sky or sent telescopes into emergency mode. But in a way that disturbed the foundation of prediction itself, the mathematical certainty we use to map the future of moving things. This is not a story about what happened. This is not a documentary about discovery or danger or the triumph of human observation. This is a story about what should not have happened at all. About an object that obeyed every law of physics perfectly, flawlessly, without question, until the moment it flew closest to us. And then, for reasons we still do not fully understand, it broke the rules. Not loudly. Not dramatically. Just enough to leave a mark in the data that will not fade, will not resolve, will not allow itself to be explained away. The most unsettling part is not the object itself. Not its speed or its composition or the fact that it came from beyond our sun's gravitational embrace. The most unsettling part is the timing. The precision of the moment when it chose to deviate. The exact window when Earth was nearest, when our gravity was strongest, when our instruments were watching most carefully. As if our presence mattered. As if proximity to our world triggered something inside a body that had been traveling through the frozen void for longer than our species has existed. As if it waited. Tonight, we follow the path of 3I/Atlas, an interstellar visitor that understood the assignment, that knew how to behave, that followed every rule we've written about how objects from other stars should move through our neighborhood. Until it didn't. Until it flew close enough to see Earth. And then, quietly, without warning, it decided to become a question we cannot answer. Interstellar objects are supposed to behave like ghosts. They are the universe's ultimate transients. Bodies that drift into our solar system from the unimaginable cold between stars, from regions of space so empty that light itself travels for years without touching anything at all. They enter our neighborhood already moving too fast to stay, already committed to leaving, their futures written in the language of gravity and momentum before they even cross the boundary where the sun's influence begins to fade into the galactic background. They trace a single hyperbolic arc, a curve so perfect, so inevitable, that you can predict where they will be centuries from now with terrifying accuracy. They do not linger. They do not slow down. They do not circle back for another look. And they certainly, absolutely, under no circumstances, do not react to their surroundings in ways that suggest awareness or response. Their trajectories are deterministic, fixed, immutable. The moment they enter the solar system, physics has already decided where they will go, how fast they will move, and when they will vanish back into the darkness beyond Pluto's orbit. There is no room for surprise. No space for deviation. No possibility of change unless something collides with them, unless a planet's gravity bends their path in ways we can calculate with absolute precision, unless the sun's radiation pressure pushes them in directions we can model and predict. 3I/Atlas understood this assignment perfectly. When astronomers first detected it, a faint point of light moving against the background stars with motion too swift to belong to anything born in our system, the numbers told a clean story. The kind of story that scientists love because it confirms everything they already know about how the universe works. Escape velocity confirmed. The object was moving faster than the sun's gravity could ever recapture. Hyperbolic orbit locked in. The curve of its path through space was open-ended, a parabola that would never close, never loop back, never return. Origin point calculated. Somewhere in the frozen dark beyond our stellar cradle, beyond the heliopause where the solar wind finally surrenders to the interstellar medium, beyond the Oort cloud where comets sleep in billion-year orbits. It was a traveler passing through, already committed to leaving before it even arrived. Already gone, in a sense, the moment we saw it. The mathematics was elegant. The predictions were precise. The future was certain, written in equations that had never lied before. And then Earth happened. Not a collision. Not a near miss that sent it spinning wildly off course. Not a gravitational slingshot that threw it toward the outer solar system or bent its path into something chaotic and unpredictable. Nothing that dramatic. Nothing that would make sense in the comfortable framework of Newtonian mechanics and gravitational perturbations. Instead, during the narrow window when 3I/Atlas flew closest to our planet, during those few hours when the distance between Earth and this ancient visitor collapsed to its minimum value, something softened in its motion. Something gave. A disagreement emerged between where the object should have been and where it actually was. Small residuals. Tiny discrepancies. The kind of thing that appears in the data like whispers in a room you thought was empty, like footsteps in a house where you know you are alone. Numbers that should have matched but didn't. Positions that should have aligned but remained stubbornly, persistently offset by amounts too large to ignore but too small to explain easily. At first, scientists did what scientists always do when reality refuses to match prediction. They assumed error. They checked everything. Instrument calibration. Were the telescopes pointing where they thought they were pointing? Atmospheric refraction. Was Earth's atmosphere bending the light in ways they hadn't accounted for? The pull of Earth's gravity, calculated to absurd, almost obsessive precision, modeled with supercomputers that could simulate the gravitational influence of every major body in the solar system down to the meter. Solar radiation pressure, the gentle push of sunlight itself, a force so weak it seems irrelevant but over vast distances and long timescales can shift trajectories in measurable ways. Systematic errors in the observation network? Were multiple telescopes all making the same mistake? Data processing artifacts. Were the algorithms that convert raw photons into positions introducing subtle biases? Every possible source of noise was examined. Every correction factor was applied. Every uncertainty was quantified and accounted for. And still, after every check and double-check and triple-check, after every possible source of error had been eliminated or reduced to levels far below what could explain the observations, the discrepancy remained. Not growing. Not fading. Not averaging out over time as random noise should. Just sitting there in the numbers like a fact that refused to make sense, like a piece of data that didn't fit anywhere in the framework of understanding that had been built over centuries of studying how objects move through space. The object had not slowed down. It had not turned sharply. It had not been captured by Earth's gravity or deflected into some wild new orbit. But it had deviated. Gently. Persistently. Undeniably. From the path that physics, all of physics, every equation we trust, every principle we've tested a million times, had promised it would follow. And the timing could not be ignored. Could not be dismissed as coincidence. Not before the Earth flyby. Not after. During. Precisely during. In the exact window when our planet's influence should have been predictable, calculable, known. Astronomy lives and dies by the elegance of curves. When you plot the motion of an object through space, when you track its position night after night and transform those observations into a mathematical description of its trajectory, you expect smoothness. You expect a line so perfect, so continuous, so free of sudden jumps or inexplicable bends that it looks like silk stretched across the dimension of time. Any deviation from that line, any bump, any wiggle, any departure from the predicted path, is either error or information. And distinguishing between the two is the entire game. Is it noise in the instruments? Or is it a real signal, a genuine piece of physics trying to tell you something you didn't know? For 3I/Atlas, the line had been perfect. Clean. Predictable. Beautiful, even in the way that mathematical objects can be beautiful when they conform exactly to theory. The observations before the Earth flyby matched the models with a kind of precision that makes scientists smile, that confirms their understanding of gravity and motion and the forces that shape the paths of objects through the void. And then the flyby happened. And residuals began appearing in the data like hairline cracks in glass, like fractures spreading through ice that looked solid from above but was under stress you couldn't see. Small differences. Tiny mismatches between where prediction said the object should be and where observation said it actually was. The kind of thing that, under normal circumstances, you would attribute to measurement noise, the random scatter of data points that happens when you're trying to measure something incredibly faint, incredibly far away, with instruments that are sophisticated but not perfect. You would assume the deviations would average out. That multiple observations would cancel the errors and reveal the true, smooth curve underneath. But this did not average out. This did not fade. Each new telescope pointed at 3I/Atlas confirmed what the previous one had seen. Each new night of observation added another data point that fell in the same wrong place, that sat on the same side of the predicted curve, that suggested the object was consistently, systematically deviating in a way that could not be explained by random error. The curve had bent. Not sharply. Not catastrophically. Not in a way that would make the object spiral into the sun or escape the solar system on some wild new trajectory. But enough. Enough that every recalculation produced the same uncomfortable result. Enough that the scientists who work with this data, people who are trained to be skeptical, who are professionally paranoid about systematic errors, who have spent careers learning to distinguish signal from noise, could not make it go away. Something was influencing this object in a way the models had not anticipated. Something was pushing or pulling or altering its motion in a manner that remained invisible to every attempt to identify the source. Scientists began searching for explanations with the kind of methodical desperation that defines good research. They constructed hypothesis after hypothesis, each one plausible, each one grounded in known physics, each one capable in theory of producing the kinds of small deviations they were seeing. Was there outgassing? The question was obvious. Some comets eject material as they warm up, as volatile ices trapped in their interiors sublimate and escape through the surface. The escaping gas acts like a rocket engine, tiny, inconsistent, but real. The force is small, but over days and weeks it can accumulate, pushing the object slightly off its predicted path in ways that depend on which direction the gas is venting and how the object is rotating. But 3I/Atlas showed no visible tail. No coma of gas and dust surrounding it like the fuzzy halos that make comets recognizable even to amateur astronomers. No brightening that would indicate fresh, volatile-rich material being exposed to sunlight. No spectral lines that would reveal the chemical signature of sublimating ice, water, carbon dioxide, methane, ammonia, any of the usual suspects. The object looked dark, inert, silent. Was there mass loss? Again, if material was leaving the surface, you would expect to see changes in brightness or spectral signature. You would expect the object to become slightly brighter as darker surface layers eroded away to reveal fresher material underneath. Or you would expect to see the scattered light from escaping particles, faint but detectable with sensitive instruments. But the photometry remained stable. The brightness didn't change in ways that suggested active mass loss. Was the object tumbling in a way that created asymmetric forces? This was more subtle. Rotation can produce strange accelerations in irregularly shaped bodies, especially if they're venting material from specific spots on the surface. As the object spins, different faces are exposed to sunlight at different times, and if one face is releasing gas while another is not, the net force changes direction with the rotation period, creating a complex acceleration pattern that depends on the object's shape, spin state, and internal structure. Possibly. The idea was plausible. But the rotation data was inconsistent. The light curve, the pattern of brightness variations over time that reveals how an object is tumbling, didn't show the clear, periodic signal you would expect from a simple rotator. And the numbers refused to settle into any stable interpretation that could fully explain the observed deviations. Every hypothesis ran into the same wall. Plausible in theory. Lacking evidence in practice. Unable to close the case. And beneath all of this technical detective work, beneath all the careful analysis and hypothesis testing and model building, sat one question that no one wanted to ask out loud, one possibility that felt uncomfortable even to consider. Why here? Why during Earth's flyby? Why not earlier, when the object was closer to the sun and experiencing far more intense radiation, when the thermal stresses should have been at their peak, when any volatile ices should have been sublimating most vigorously? Why not later, after it had moved into the outer solar system where temperature gradients might trigger delayed reactions, where buried ices might finally reach the surface and begin venting? Why in the narrow window where we were closest? Where Earth's gravity was strongest? where our instruments were watching most carefully, where our planet's influence, gravitational, magnetic, thermal, was at its peak. The timing was too precise, too correlated, too difficult to dismiss as coincidence. Earth is not a passive observer in this cosmic drama. It is not a neutral platform from which we simply watch the universe unfold. Its gravity extends far beyond the thin shell of atmosphere that makes life possible, reaching out into space with invisible fingers that sculpt the paths of satellites in low orbit, that perturb asteroids passing nearby, that can capture dust particles and drag them slowly downward over years and decades. But these effects are known. They are calculable. They are predictable to absurd levels of precision, the kind of precision that lets us land spacecraft on distant moons after years of travel through the solar system, that lets us predict eclipses centuries in advance, that lets us navigate the crowded orbital environment around Earth without collisions. When 3I/Atlas flew by, Earth's gravitational influence was measured with every tool available to modern astronomy. The mass of Earth, known to 11 significant figures. The distance at closest approach, measured to within meters using parallax observations from multiple telescopes around the globe. The expected deflection calculated using general relativity, though at these speeds and distances Newtonian mechanics would have been more than sufficient. Every trajectory calculation included Earth's gravity. Every model accounted for the planet's pull. And the predicted deflection matched observation almost perfectly. Almost, but not quite. There was something additional. Something extra. Not dramatic. Not a capture event that would have bent the object's hyperbolic path into an ellipse and trapped it in orbit around Earth. Not a violent perturbation that would have sent it careening off in some wildly different direction. Something softer. Something subtler. Something that felt less like a mechanical interaction, gravity pulling on mass in the straightforward, deterministic way that Newton described, and more like a response. As if the object had reacted to something. As if Earth's presence triggered a change inside the visitor that went beyond simple gravitational deflection. Scientists began exploring stranger possibilities, ideas that lived on the edge of mainstream physics, hypotheses that would never have been considered if the data hadn't forced them to look beyond the comfortable explanations. Could Earth's magnetosphere have interacted with 3I/Atlas in an unexpected way? The magnetosphere is a bubble of magnetic field that surrounds Earth, deflecting the solar wind and protecting the atmosphere from erosion by charged particles. It's complex and dynamic, constantly shifting in response to changes in solar activity, extending tens of thousands of kilometers into space on the day side and stretching into a long tail on the night side. If 3I/Atlas carried any residual charge, if its surface had been modified by exposure to cosmic rays during its long journey through interstellar space, could the magnetic field have exerted forces that wouldn't show up in standard gravitational calculations? Could the solar wind, compressed and redirected by our planet's magnetic field into complex structures, bow shocks, magnetosheath, plasma sheets, have struck the object differently than it would have in open space? Could the impact of charged particles, concentrated and accelerated by magnetic fields, have ablated material from the surface or triggered subsurface volatiles to vent? Could tidal forces have mattered? Tidal forces are differential gravitational effects. The fact that gravity pulls slightly harder on the near side of an object than on the far side. 4 large moons orbiting close to planets, tidal forces can be enormous, powerful enough to generate internal heat through friction, powerful enough to tear bodies apart if they cross the Roche limit. But for a small object making a distant flyby, tidal forces should be negligible. Unless the object was unusually fragile. Unless its internal structure was held together weakly, with strength barely sufficient to resist even modest stresses. Unless it contained voids or cracks or layers of material with different mechanical properties that could shift and slide when subjected to differential forces. Could tidal forces, tiny, almost irrelevant in ordinary circumstances, have triggered internal stresses that led to delayed outgassing, to fractures opening and releasing trapped gases hours or days later when the object was no longer at closest approach? These were not the kind of hypotheses you write with confidence. These were not ideas you publish in high-impact journals without extensive evidence. They were uncomfortable speculations, the kind that suggest physics might behave differently when applied to objects born under other stars, when applied to materials forged in environments we've never sampled, when applied to bodies whose histories span timescales that dwarf the age of our entire species. Because 3i/Atlas was not built here. That single fact changes everything. It alters every assumption. It undermines every comfortable analogy. Its materials were not forged in the disk of gas and dust that collapsed to form our sun and planets. They were created in the stellar nursery of a different star, perhaps one that burned hotter or cooler, one that emitted a different spectrum of light, one that bathed its protoplanetary disk in radiation environments we can only guess at. Its ices are not our ices. Water ice formed in the outer solar system has specific properties: crystal structure, isotopic ratios, trapped gases, that reflect the conditions under which it condensed. But water ice formed around a different star might be different. The ratio of deuterium to hydrogen might be higher or lower. The temperature at which it formed might have been colder or warmer. The impurities mixed into the ice, salts, organics, silicates, might have completely different compositions. Its minerals were shaped by processes we've never observed. Rocks and grains that condensed from a protoplanetary disk with a different chemical makeup, that were processed by heating and cooling cycles driven by a star with different luminosity, that collided and fractured and sintered together under gravitational conditions that may have been subtly different from what happened in our own system. Its internal structure evolved over millions or billions of years in the absolute cold of interstellar space. No sunlight to heat one side and create thermal gradients. No stellar wind to erode the surface. No planets nearby to generate tidal stresses. Just the background radiation of the universe, 3 degrees above absolute zero, and the occasional impact from a high-speed interstellar dust grain or cosmic ray. Time enough for the internal structure to relax, to settle, to reach thermal equilibrium in ways that objects in our solar system never do because they're constantly being perturbed by the sun's heat and the gravitational tugs of planets. And then it entered our solar system. And everything changed. Everything. Radiation intensity increased by orders of magnitude. The faint background glow of the universe was replaced by the blazing output of a star that, while still far away, was vastly brighter than anything the object had experienced in its interstellar wandering. Photons began striking the surface by the trillions per second, heating it, creating thermal gradients between sunlit and shadowed regions, driving sublimation of surface ices that had been stable for eons. The density of particles increased. The solar wind, a stream of charged particles flowing outward from the sun at hundreds of kilometers per second, struck the object with forces it had never felt before. Protons, electrons, alpha particles, heavier ions, all carrying energy and momentum, all capable of sputtering atoms from the surface, all interacting with whatever surface chemistry or trapped gases might be present. Gravity stopped being a distant, uniform pull from the galaxy and became complex, multi-bodied, dynamic. First the sun's gravity, growing stronger as the object fell inward, bending its trajectory in ways that required constant recalculation. Then the gravitational fields of Jupiter, Saturn, the other giant planets, weak but non-negligible, pulling in different directions at different times, creating a complex web of forces that depended on the relative positions of all the bodies involved. And then Earth. Close. Sudden. A gravitational encounter that lasted only hours but during which the forces on the object changed rapidly, creating accelerations, tidal stresses, perturbations that rose and fell as the geometry of the flyby evolved. The flyby of Earth was not just a moment of closeness. It was not just a point on the trajectory where two objects happened to pass near each other in the vastness of space. It was a moment of environmental shock. A transition from one regime to another that happened too quickly for the object to adapt, too quickly for internal temperatures to equilibrate, too quickly for stresses to dissipate through slow structural adjustments. Like a deep-sea organism brought suddenly toward the surface, like a piece of frozen tissue thrust into warm air, 3i/Atlas may have experienced changes it had never encountered before and was not equipped to handle. Internal fractures could have widened as thermal expansion fought against the rigidity of materials that had been cold for billions of years. Volatile materials trapped beneath a dark, radiation-processed surface crust could have begun sublimating as heat conducted inward from the sun-warmed exterior, building pressure until weak spots ruptured and gas escaped in brief, invisible bursts. Phase changes could have occurred deep within the object, solid to gas without passing through liquid, transitions that absorb heat and shift mass and alter the distribution of density inside the body. The idea that Earth's neighborhood, its gravity, its magnetic field, its position in the solar system where radiation intensity and particle density and thermal gradients all take specific values, could awaken dormant processes inside an interstellar body was not comforting. It was not the kind of idea that made scientists feel they understood what was happening. It suggested interaction without contact, influence without intention, a kind of passive agency where Earth's mere existence was enough to change something ancient and alien, where proximity alone could trigger responses in an object that had traveled across light years of empty space without reacting to anything at all. It blurred the line between observer and participant in ways that felt philosophically unsettling. And yet, the sky remained silent. The void offered no visible confirmation. If something changes inside a comet or asteroid, if internal processes shift, if volatiles begin sublimating, if structure fractures and material escapes, we expect to see it. A tail forms. Gas and dust ejected from the nucleus are pushed away by solar radiation pressure and the solar wind, creating the characteristic streaming appearance that makes comets instantly recognizable. A coma appears. A fuzzy halo of scattered light surrounds the object as escaping gas carries dust particles outward, creating an atmosphere that can extend for tens or hundreds of thousands of kilometers. Brightness increases. Fresh material exposed to sunlight has different reflective properties than the dark, radiation-processed crust that accumulates over time on objects in space, and even small amounts of new material can cause measurable brightening. But 3I/Atlas refused to cooperate with these expectations. It offered no spectacle. No plume of gas followed it like a banner trailing behind a ship. No sudden brightening betrayed hidden activity beneath the surface. No tail stretched across the sky, no coma glowed softly in scattered sunlight. Astronomers did not give up easily. They stacked hundreds of images, combining exposures to reach deeper into the noise, to reveal faint structures that might be invisible in any single observation. They enhanced contrast, applied digital filters designed to bring out subtle variations in brightness that the eye would miss. They used instruments capable of detecting emissions at wavelengths where certain gases fluoresce when excited by sunlight, ultraviolet detectors sensitive to hydroxyl radicals, infrared cameras tuned to see carbon dioxide and water vapor. They searched for even the faintest halo of escaping particles, for any deviation from a perfect point source that would indicate the object was surrounded by ejected material. If there was activity, if something was happening inside or on the surface of 3I/Atlas, it was happening in a way our eyes and cameras were not trained to detect. Perhaps gas without dust. Volatile molecules escaping into space but carrying too few solid grains to scatter visible light efficiently, creating a plume that would be invisible optically but might show up in ultraviolet spectroscopy or radio observations of molecular emissions. Perhaps microfractures venting briefly before sealing shut again. Pressure building, cracks opening, gas escaping for minutes or hours before the fractures closed as temperatures dropped or internal pressures equalized, creating bursts too short-lived and too faint to catch unless you happen to be watching at exactly the right moment. Perhaps mass redistribution rather than mass loss. Internal shifts that changed the object's balance, that altered how it rotated or how its mass was distributed, without ejecting significant amounts of material into space. Perhaps the activity was hidden beneath the surface entirely, occurring in subsurface voids and fractures where our instruments cannot see, manifesting only through subtle changes in rotation or tiny accelerations that show up in the trajectory data but nowhere else. The absence of visible evidence became its own kind of evidence. Not proof that nothing was happening. Absence of evidence is not evidence of absence, but proof that whatever was happening was subtle, hidden, occurring on scales or at wavelengths or in ways that our current observational capabilities were not optimized to detect. In space, silence is not emptiness. It is not confirmation that nothing exists. It is often concealment. Concealment by scale, phenomena too small to see directly. Concealment by wavelength, emissions at frequencies our detectors are not sensitive to. Concealment by timing, events that happen too quickly or too slowly for our observation cadences to catch. Concealment by the fundamental limits of what we have built to see, the instruments and techniques we've developed based on studying objects formed in our own solar system that may not be adequate for understanding visitors from elsewhere. Every small body in space spins. Rotation is universal, a fingerprint of the object's history written in its motion. Ancient collisions that imparted angular momentum. Chaotic gravitational interactions during formation when countless small bodies were accreting and fragmenting and merging in the chaotic early solar system. Or in the case of interstellar objects, in whatever distant stellar system gave them birth. Gravitational tugs from long-forgotten encounters with planets or other large bodies that torqued the object and changed its spin state. The rotation of a small body carries information. The period tells you how fast it's spinning. The amplitude of brightness variations tells you how non-spherical it is, how much its cross-section changes as different faces are illuminated. The shape of the light curve, smooth or irregular with deep minima or shallow variations, reveals details about shape, surface reflectivity, possibly even large-scale topographic features like craters or facets. After the Earth flyby, subtle changes appeared in the brightness variations of 3I/Atlas. Nothing dramatic. No wild swings from bright to faint that would indicate the object had started tumbling chaotically. But irregularities. Deviations from the pattern that had been observed before the flyby. The light curve, the graph of apparent magnitude versus time, the record of how bright the object appeared from Earth as it rotated, began showing features that hadn't been there earlier. Not wild fluctuations but slight changes in the timing of maxima and minima, small shifts in amplitude, hints of additional periodicities that might indicate the rotation was becoming more complex. The changes suggested the object might be tumbling rather than rotating smoothly around a single axis, or that its mass distribution had changed enough to alter how light reflected off its surface. Tumbling motion is more complex than simple rotation. Instead of spinning around one stable axis like a well-balanced top, a tumbling body rotates around multiple axes simultaneously, its orientation in space following a complicated path that depends on its shape and internal mass distribution. The light curve of a tumbling object is typically more irregular, harder to predict, showing variations on multiple timescales as different aspects are illuminated. Rotation-driven forces can produce tiny accelerations over time, especially in bodies with irregular shapes. This is well established. As the object spins, if it's venting material, gas or dust escaping from specific locations on the surface, the direction of the thrust changes with the rotation. The net effect depends on the rotation period, the location and strength of the venting, the shape of the body, and many other factors. But over days and weeks these tiny forces can accumulate and produce measurable changes in trajectory. The so-called YRP effect, Yarkovsky-Okifradzievsky-Paddock effect, and its variants describe how thermal emission and reflected sunlight can torque small bodies and change their spin states over long timescales. But once again, like a refrain that will not fade, timing haunted every interpretation. Why did these changes in the light curve, these hints of altered rotation or mass distribution, appear after the Earth flyby? Why not earlier, when the object was closer to the Sun and experiencing peak thermal stress, when temperature gradients should have been strongest, when any shape-changing or spin-altering processes driven by solar heating should have been most active? Why not later, as it cooled and settled, as thermal stresses relaxed and internal temperatures equilibrated? Why now? Why in correlation with the one event that should have been purely gravitational, purely predictable, purely understood? The idea formed quietly, reluctantly, among those who study these things, spoken in private conversations and cautious emails, not yet ready for formal publication but persistent enough that it could not be dismissed. Perhaps the flyby altered the object's internal stress distribution enough to change how it spins. Perhaps the tidal forces, small, almost negligible but real, opened fractures or shifted internal layers just enough that the principal axis of rotation changed slightly. Perhaps trapped volatiles released during the flyby redistributed mass inside the body, moving the center of mass and altering the moments of inertia that determine how the object responds to torques. Not dramatically. Not violently. Not in a way that would shatter the object or send pieces flying off into space. Just enough. Just enough to matter. Just enough to show up in the light curve as subtle irregularities that persistent, that suggest something inside 3I/Atlas is not quite the same as it was before it met Earth. We often imagine interstellar visitors as relics. We picture them as frozen snapshots from elsewhere, as unchanging messengers carrying information about distant star systems preserved in their pristine, unaltered state. Museum pieces drifting through the void. Time capsules that have remained unchanged since they formed billions of years ago in protoplanetary disks around stars we will never see. We want them to be fossils, static and readable, bodies we can study to learn about conditions in other parts of the galaxy without worrying that the act of observation might change what we're observing. But perhaps that image is wrong. Perhaps it has always been wrong, and we only believed it because we had no data to contradict it, because interstellar objects were theoretical curiosities for so long that we could imagine them however we wanted. Perhaps interstellar objects are not static at all. Perhaps they are not frozen relics but dynamic archives, active bodies that respond to every new environment they cross, that evolve as they travel, that record interactions in their structure and motion and chemistry in ways we are only beginning to understand. Perhaps they change as they pass through different radiation environments, as they experience different particle fluxes, as they enter the gravitational wells of different stars and feel forces they haven't felt in millions of years. Perhaps they react. Perhaps they are not passive witnesses to the universe but participants in it, altered by every significant encounter, shaped by every star system they traverse. If this is true, and the behavior of 3I/Atlas suggests it might be, then nothing we observe about an interstellar object represents its original state. By the time we detect it, by the time our telescopes can track it and our instruments can measure it, it has already changed. It has already been processed by our sun's radiation. It has already felt the push of the solar wind. It has already been heated and stressed and possibly fractured in ways that would never have happened if it had remained in the cold, quiet darkness between stars. 3I/Atlas may not be doing anything insane in the dramatic sense. It may not be violating the laws of physics or behaving in ways that require new fundamental theories. It may simply be revealing something far more unsettling than a violation of physics could ever be. It may be showing us that interstellar bodies are not passive, that they interact with the systems they pass through in ways we are only beginning to measure, in ways our models were not built to predict because those models were developed by studying objects that never left our solar system, that never experienced the transition from interstellar space to the intense environment close to a star. That every close encounter becomes an experiment, one we didn't know we were running, one we didn't design, one whose results we're only now beginning to analyze and whose implications we don't fully understand. If this is true, then every future interstellar visitor carries the same potential for surprise, the same capacity to react in ways our local experience has not prepared us for. And if our presence, Earth's gravity, Earth's magnetosphere, Earth's position in space where radiation and particles and thermal gradients all take specific values that may be rare or unusual in a galactic context, can trigger changes in objects born light years away, then the universe is more connected than we thought. More interactive. More reactive. More alive with invisible conversations, with subtle exchanges of energy and momentum and information that flow through the fabric of space itself, linking star systems across distances so vast that light takes years to cross them, creating a web of influence that operates on scales we're only beginning to perceive. Our models are built on what we know. This is not a criticism. It is simply a fact, an unavoidable consequence of the scientific method itself. You build theories based on observations. You test those theories against new data. You refine your models to explain what you see. But the models are always, necessarily, limited by the range of phenomena you've observed, constrained by the examples you've studied, shaped by the implicit assumption that the sample you have is representative of the universe as a whole. Asteroids formed here, in this solar system, under this sun's light, from the same disk of gas and dust that collapsed and accreted to make Earth and the other planets. We've studied thousands of them. We've sent spacecraft to orbit and land on several. We know their compositions, their densities, their internal structures, at least for the ones we've examined up close. Comets formed here, in the cold outer regions of the solar nebula or in the Oort cloud at the edge of the sun's gravitational influence. We've watched them brighten as they approach the sun. We've seen their tails form and dissipate. We've measured their outgassing rates and analyzed the composition of the gases and dust they release. We've even rendezvoused with them, placing spacecraft in orbit and landing probes on their surfaces. Our understanding of orbital mechanics, how gravity shapes trajectories, how solar radiation pressure pushes on small objects, how thermal forces can produce tiny accelerations, is filtered through familiarity. Through objects that grew up in the same stellar neighborhood we call home. Objects that formed under conditions we can study directly, that have been processed by a star we can observe in detail, that have interacted with planets whose masses and orbits we know precisely. Interstellar objects challenge that comfort. They are not from here. They did not form under conditions we can easily study. They were not shaped by our sun's radiation or our planet's gravitational fields. They come from environments we can only infer indirectly, from stellar systems we may never be able to observe in enough detail to understand their protoplanetary disk conditions, their planet populations, their radiation environments. When 3I/Atlas deviated from expectation, when its motion refused to match the predictions generated by models built on our local experience, it did not just pose a scientific puzzle, a question to be answered with more data and better calculations. It exposed the edges of our assumptions. It revealed the boundaries where knowledge ends and guesswork begins, where the comfortable framework built from decades of studying local objects might not apply, where the universe in its full diversity might behave in ways we haven't witnessed because our sample size is still, despite all our progress, still pitifully small. Perhaps nothing insane happened at all. Perhaps the word insane is itself a reflection of human psychology, our tendency to label as abnormal anything that violates our expectations, anything that falls outside the narrow range of behaviors we've observed often enough to consider familiar. Perhaps 3I/Atlas behaved exactly as interstellar objects always behave when they pass close to planets, and we're only surprised because we've never had the instruments or the opportunity to watch it happen before. Perhaps our definitions of normal are simply too narrow, built on a sample size of one star system, ours, and shaped by the parochial assumption that what happens here must happen everywhere, that the patterns we've observed among solar system bodies are universal rather than local, that physics operates the same way regardless of where an object formed or what history it carries. But that realization does not calm the mind. It does not resolve the mystery or make the data easier to interpret. Instead, it expands uncertainty. It opens the door to possibilities we cannot yet name, to categories of behavior we haven't observed, to interactions between interstellar visitors and planetary systems that might be common throughout the galaxy but that we're only now barely beginning to detect. It suggests that the universe is larger and stranger than our models can currently accommodate. Before the Earth flyby, 3I/Atlas was a curiosity. An interesting object, certainly. Worth studying, worth tracking with as many telescopes as could be brought to bear. Another interstellar visitor to catalog, measure, and compare to the handful of others we detected in recent years. Scientists would observe it carefully, take spectra to determine its composition, measure its rotation to infer its shape, track its trajectory to refine our understanding of its origin. Papers would be written. Data would be archived. The object would take its place in the growing list of interstellar bodies that have passed through our solar system, adding one more data point to the sparse sample we're building of what else is out there. After the flyby, it became a question. Not just an object but a mystery. Not just a data set but a problem that refused to be solved. A puzzle that remained stubbornly incomplete no matter how much analysis was applied to it. Not because it threatened us. It poses no danger, no risk of impact, no dramatic consequence for Earth or any other planet in the solar system. Its trajectory carries it away from the Sun, out into the outer solar system and eventually back into interstellar space, and nothing will prevent that departure. We are safe. But that safety does not eliminate the unease. Because 3I/Atlas reacted. Something about passing near Earth mattered. Something about proximity to our world, our gravity, our magnetic field, our position in space, our mere presence, triggered a change, however subtle, in an object that should have been immune to our influence. An object that had traveled across light years without changing, that had passed through regions of space where radiation is vanishingly faint and particles are almost non-existent, that had maintained whatever structure and composition it was born with through timescales that dwarf human history. And then it came close to Earth, closer than the Moon, though still far enough that collision was never a possibility, and something shifted. The math says so. The residuals in the trajectory data say so. The changes in the light curve say so. And once that possibility enters the scientific conversation, once you allow yourself to consider that Earth's presence triggered a response in this ancient visitor, it cannot be removed. It cannot be dismissed as error or coincidence or misinterpretation, because it suggests a universe where interaction happens even without contact, where influence flows through the fabric of space and time in ways we are only beginning to measure, where gravitational fields and magnetic fields and thermal radiation reach out across the void and touch things that were never supposed to be touched, where nothing truly passes through a system unchanged. The flyby became a mirror. It reflected back not just data about a distant visitor but uncomfortable truths about the limits of our understanding, about the naive assumptions we've made in building our models of how the universe works, about the quiet, unseen forces shaping reality around us that we've been blind to simply because we lack the sensitivity and the opportunity to observe them. It transformed 3I/Atlas from a scientific curiosity into a philosophical challenge, from an object to be measured into a question about the nature of space itself. We label moments as insane because they break our expectations. We use words like crazy and impossible and shouldn't have happened, when reality refuses to conform to prediction, when the universe does something we weren't prepared for, when our models fail in ways that feel personal, as if nature has betrayed us by not following the rules we thought we understood. But expectation is a human construct. It is a mental model we build to feel secure in a chaotic universe, a framework of assumptions and predictions that lets us navigate reality without being paralyzed by uncertainty. The cosmos does not care about our expectations. It does not pause or apologize when something surprises us. It does not adjust its behavior to match our theories or make itself easier to understand. It simply is what it is, operating according to laws we're still discovering, exhibiting phenomena we haven't yet named, creating patterns on scales we've barely begun to perceive. And yet, the timing of what happened to 3I/Atlas matters to us deeply. It matters in a way that transcends scientific curiosity, in a way that feels almost emotional. Because Earth was there. We were there. Watching with every telescope we could aim at the sky, recording data with instruments sensitive enough to detect changes in position smaller than the diameter of a grain of sand on a beach halfway around the world, measuring brightness variations smaller than what the human eye can perceive. We were present. We were witness. We caught this moment not through luck or accident but through deliberate observation, through networks of telescopes coordinated across multiple continents, through decades of investment in instruments and techniques specifically designed to track faint objects moving through the solar system. We were present for the moment when this ancient traveler from beyond our sun's domain, from regions of space so distant that their light has not yet reached us, from star systems that may no longer exist in the forms they had when this object was born, chose or was forced to deviate. The word chose is wrong, of course. Objects don't choose. They don't have agency or intention. They simply respond to forces according to the laws of physics. But the data makes it feel like a choice. The timing makes it feel like something more than mechanical response. The correlation between proximity to Earth and deviation from prediction creates a narrative that our pattern-seeking brains cannot help but construct. A story where causation seems clear even if mechanism remains hidden. That presence, our presence, Earth's presence, transforms the event from an abstract curiosity into a personal mystery. From something that happened somewhere in the solar system into something that happened here, to an object that came near us, during a flyby that involved our world directly. Because if our planet can influence something so far from home, so disconnected from our history, so fundamentally alien in origin and composition, then the boundaries we draw between here and there, between us and the rest of the universe, between local and distant, are more porous than we imagined. More permeable. More fictional. We like to think of Earth as an island in space, isolated and safe, our little pocket of warmth and life surrounded by cold vacuum that buffers us from the rest of the cosmos. But 3I/Atlas suggests that isolation is an illusion, that our gravitational field reaches far beyond our atmosphere, that our magnetic field touches objects we will never see, that our simple presence in this region of space matters, creates conditions that affect passing visitors, leaves marks in the trajectories of bodies that will carry those marks out into interstellar space, spreading news of our existence to regions so distant that light from Earth has not yet reached them. Each interstellar visitor rewrites a rule. Oumuamua was first. The moment we confirmed its hyperbolic orbit, the moment we proved beyond doubt that it came from beyond the sun's gravitational domain, everything changed. Interstellar objects transformed from theoretical possibility to observed reality. They were no longer just ideas in papers or results from computer simulations predicting how often objects should be ejected from other star systems and wander through the galaxy. They were real. They were here. We could observe them, track them, measure them, learn from them. Oumuamua taught us that hyperbolic orbits are not just mathematical abstractions but physical realities, that objects from other stars truly do wander through our neighborhood, that the galaxy is not a collection of isolated star systems but a connected web where matter flows between systems over timescales of millions and billions of years. Borisov came next, and it taught us a different lesson. It showed us that some interstellar visitors look familiar, that not everything from beyond is strange and alien. Borisov had a tail. It had a coma. It brightened as it approached the sun. It outgassed in ways that matched comets formed in our own solar system. Its spectrum showed water, carbon monoxide, cyanide, the usual suspects, the molecules we expect from cometary ice. It looked, in almost every measurable way, like our comets. It suggested that whatever processes create comets around our sun might be universal, that protoplanetary disks around other stars might not be so different from the one that formed our solar system, that perhaps the basic chemistry and physics of planetary formation produces similar outcomes regardless of where it happens. 3i/Atlas may be continuing that pattern of revelation, not by being dramatically different from everything that came before, but by being subtle. By showing us something we might have missed if we weren't looking carefully enough, if our instruments weren't sensitive enough, if we hadn't developed the techniques to detect deviations so small they would have been lost in noise just a decade ago. By demonstrating that closeness matters even when collision does not occur, even when gravitational deflection is predictable and well understood. By revealing that the environment around a planet, the gravitational field, the magnetic field, the thermal radiation, the complex interactions between solar wind and magnetosphere, can reach out and touch things in ways that leave measurable traces. By proving that even a distant flyby can be an interaction, that even a glancing passage can trigger responses, that even objects moving too fast to be captured can still be changed by their brief encounter with our world. Each visitor adds another data point to a pattern we are only beginning to perceive, another clue in a mystery we're only starting to understand. A pattern about how interstellar space connects star systems not just through gravity and light but through the exchange of material, through the sharing of objects that carry information about their origins, through interactions that happen when these wanderers pass close to stars and planets they've never encountered before. Another clue to how common these objects are. Estimates based on just a handful of detections suggest the galaxy contains trillions of interstellar objects wandering between the stars, far more than the total number of objects in any single star system. Another piece of evidence about how star systems are not closed systems but open ones, constantly exchanging matter with their galactic neighborhoods, shaped not just by their own internal dynamics but by visitors from elsewhere that pass through and leave their own subtle influences. Perhaps the most important change occurred where our instruments cannot look. This thought haunts the scientists who study 3i/Atlas more than any other. Because we can measure trajectories. We can track positions across the sky and convert those observations into velocities and accelerations. We can measure brightness and spectra and polarization. We can image the object, though at these distances even our best telescopes show it as nothing more than a point of light, a single pixel against the background stars. But we cannot see inside. We cannot peer beneath the surface to see what's happening in the interior, in the hidden regions where the real story might be unfolding. Inside the object, in spaces no telescope can reach, changes could be occurring that dwarf anything we've measured. Along microscopic fractures that opened when tidal forces pulled one side harder than the other, when the differential gravitational pull across the body created stresses that exceeded the strength of whatever material held the structure together. These fractures might be tiny, hairline cracks nanometers wide, but there could be billions of them, a network of damage spreading through the interior like cracks in ice, weakening the structure, allowing volatiles to migrate through pathways that didn't exist before. Within volatile pockets sealed for eons, trapped since the object's formation or since the last time it experienced significant heating from a close pass to a star. Pockets of ice, water, carbon dioxide, methane, ammonia, nitrogen, that have remained solid and stable at the 3-degree background temperature of interstellar space but that might begin sublimating when heated by even a few degrees, when exposed to pressures that change as fractures open and close, when triggered by phase transitions that propagate through the interior like a slow-motion explosion. Phase changes could be occurring deep within the object. Solid to gas without passing through liquid, sublimation driven by temperature increases too subtle to measure from outside but significant within the body's interior. Or solid to liquid in eutectic mixtures where multiple compounds lower each other's melting points, creating pockets of liquid that migrate through cracks and refreezes in new locations, redistributing mass and changing the internal structure. Or structural transitions in crystalline materials, low-temperature phases converting to high-temperature phases, amorphous solids crystallizing, changes that absorb or release heat and alter material properties in ways that affect how stress propagates through the body. In crystal lattices that shifted as thermal gradients moved through alien minerals, crystals that formed under conditions we've never replicated in laboratories, that have physical properties we can only guess at, that might respond to heating and stress in ways that terrestrial minerals do not. thermal expansion coefficients we've never measured, fracture toughness values we don't know, elastic moduli that determine how cracks propagate, how much strain the material can withstand before failing, how quickly stress relaxes after a perturbation. Earth's flyby may have been the key that turned a lock we didn't know existed. The brief period of enhanced gravitational stress, the thermal pulse from being slightly closer to the sun, the possible interaction with Earth's magnetosphere, these could have combined to trigger processes that had been dormant, locked in place by cold and equilibrium, waiting for just the right combination of conditions to activate. Processes that had been waiting since before our species learned to walk upright, since before multicellular life arose on Earth, since before the sun itself had planets. And if those changes are happening inside, hidden from view in the lightless interior of a body that might be porous and fractured and barely held together, then what we measure on the outside, the tiny deviations in trajectory, the subtle shifts in rotation, the absence of visible activity, are only shadows. Surface manifestations of transformations we cannot directly see. The data becomes a whisper of something larger, a hint that something profound is occurring in the dark heart of 3I/Atlas, in regions our instruments will never penetrate, in spaces that will remain forever mysterious unless we can somehow intercept an interstellar object before it leaves and send a probe to examine it up close. The numbers are trying to tell us a story, but we can only read the prologue. The full narrative is playing out where we cannot watch, and we are left to infer and guess and build models from incomplete information, always aware that the truth might be far stranger than anything we can imagine from external observations alone. We like to believe that space is empty. This belief is comforting. It allows us to imagine vast distances as buffers, voids that separate star systems and protect them from unwanted interactions. It supports a mental model where celestial mechanics is clean and simple, where objects follow predictable paths through vacuum, where gravitational interactions are the only forces that matter and those forces are well understood, calculable, deterministic. Most of the universe is void, we tell ourselves. Most objects pass through that void without touching anything or being touched. Collisions are rare. Close encounters are unusual. Most of the time, matter moves through space alone, isolated, following trajectories shaped only by distant gravitational fields, spending millions of years crossing the light years between stars without experiencing anything that could be called an interaction. But 3I/Atlas suggests otherwise. It suggests that this comfortable picture is incomplete at best, misleading at worst. It suggests that even brief closeness can matter, that even encounters too distant to be called close in any ordinary sense can still leave marks, can still trigger changes, can still matter in ways we're only beginning to measure. That nothing passes through a star system completely unchanged, that every object that enters is processed, heated by stellar radiation, pushed by stellar wind, deflected by gravity, exposed to particle fluxes and magnetic fields and thermal gradients that did not exist in interstellar space. That every encounter, no matter how glancing, no matter how brief, leaves a mark. On the visitor, obviously, we've measured that mark in the trajectory of 3I/Atlas, in the residuals that refuse to disappear. On our data, filling our archives with observations that don't quite match predictions, forcing us to develop new models and consider new possibilities. On our understanding of what is possible, expanding the boundaries of known behavior, adding new categories to our taxonomy of cosmic phenomena. There is a quiet fear in this realization. Not the fear of danger. Not the visceral, immediate fear of threat or collision or harm. 3I/Atlas will not hit Earth. It poses no danger to our planet or any other body in the solar system. Its trajectory is clearly hyperbolic. It is leaving and will not return. But there is a different kind of fear. A philosophical unease. The fear of connection. The fear that we are not as isolated as we thought, as we wanted to believe. That our corner of space is not separate from the rest of the galaxy, not insulated, not protected by vast distances from influences we don't understand. That we are part of something larger. A web of interactions that connects all star systems, that operates on scales we've barely begun to perceive, that means our actions and even our simple presence ripple outward in ways we cannot predict or control. The fear that influence flows in all directions through the dark. Not just from distant stars to us, their light reaching our telescopes, their gravitational fields pulling on our sun, their ejected objects entering our system, but from us outward. Our gravity reaching across space. Our magnetic field creating disturbances in the solar wind that propagate outward at hundreds of kilometers per second. Our thermal radiation adding photons to the cosmic background that will travel forever unless they strike something. Earth is not a passive observer. Earth is a participant. And that participation has consequences we are only beginning to understand. What do we call a body that behaves this way? The question is not rhetorical. Classification matters in science. It helps us organize knowledge, communicate efficiently, identify patterns across populations of objects. But sometimes classification reveals our ignorance rather than our understanding. Sometimes the categories we've built are too narrow to accommodate reality. 3I/Atlas is not quite a comet. Comets have tails. Comets have comets. Comets brighten dramatically as they approach the sun, their surfaces erupting in jets and fountains as buried ices finally reach temperatures where they can sublimate. Comets are predictably unpredictable, their trajectories altered by the rocket-like forces of outgassing in ways that require complex modeling but that follow understandable patterns. 3I/Atlas shows none of these characteristics. It remains dark, silent, visually inactive. If it is outgassing, the activity is so faint that our best instruments cannot detect it. And yet it deviates from its predicted path in ways that suggest something is influencing its motion. 3I/Atlas is not quite an asteroid. Asteroids are solid, rocky or metallic, stable over timescales of billions of years. Their trajectories change only when they collide with something or when they pass close enough to a planet that gravitational perturbations become significant. Asteroids don't react to their environments. They don't change their motion in response to heating or cooling or magnetic fields. They simply obey Newton's and Einstein's equations, following paths carved through spacetime by gravity alone. 3I/Atlas obeys those equations too, almost, but not quite. The residuals suggest that something additional is happening, something that pure gravitational dynamics cannot explain. 3I/Atlas is not a threat. It never was. It never will be. Its closest approach to Earth was far beyond any distance that could be considered dangerous. Its trajectory carries it away from the inner solar system, out toward the Kuiper Belt and beyond, and eventually back into interstellar space where it will resume its journey through the galaxy. In thousands of years, it will be light years away, traveling through regions we cannot observe, perhaps eventually passing through another star system where it will interact with that system's planets and magnetic fields and radiation environment in ways we will never witness. But if it is not a comet, not an asteroid, not a threat, then what is it? Something else. A category we are still learning to define. A classification that doesn't yet exist in our taxonomy because we haven't observed enough examples to know what characteristics define the category, what behaviors are typical, what predictions we should make for the next object like this that passes through. A body that reacts without spectacle, that evolves in response to environments it was never designed for. Designed is the wrong word, nothing in space is designed, but the implication is clear. Environments different from the one where it formed, conditions it never experienced during its formation and early evolution. A body that carries within itself the capacity to surprise us simply by being near, by passing through our neighborhood, by interacting with Earth in ways too subtle for our eyes but detectable by our instruments. 3I/Atlas is a reminder that classification is not discovery. That naming something does not mean we understand it. That the act of putting an object into a category is not the same as explaining its behavior or predicting its future. That the universe contains phenomena we have not yet witnessed, behaviors we have not yet categorized, objects we have not yet learned to predict, interactions we have not yet thought to model. Each new interstellar visitor forces us to expand our taxonomy, to create new categories or blur the boundaries between old ones, to acknowledge that nature is more diverse than our classification schemes can accommodate. The sun shapes everything in this system. This is fundamental. Its light heats surfaces, driving the thermal processes that sublimate ices and crack rocks and create the temperature gradients that power atmospheric circulation on planets and outgassing on comets. Its gravity holds planets in their orbits, binds the solar system together, determines which objects remain bound and which escape into interstellar space. Its magnetic field extends outward, carried by the solar wind, filling the heliosphere with a complex structure of field lines and current sheets and plasma regions that interact with planetary magnetospheres and affect how cosmic rays penetrate into the inner system. The sun dominates. It is the primary influence on everything that happens within its gravitational domain. But Earth perturbs. Earth adds complexity. Earth is not just a passive recipient of solar radiation and solar wind. It creates its own environment, its own pocket of altered space. Its gravity, though tiny compared to the Sun's, is still significant at close range, strong enough to hold the Moon in orbit, strong enough to capture satellites and space debris, strong enough to deflect passing objects. Its magnetic field, generated by motions in the liquid iron core, creates the magnetosphere, a bubble of trapped charged particles and field lines that extends tens of thousands of kilometers into space, that shields the surface from harmful radiation, that creates auroras when solar wind particles funnel down along field lines and collide with atmospheric molecules. Its thermal radiation, the infrared glow of a planet warmed by sunlight and by internal heat from radioactive decay, adds photons to the environment that can be absorbed by passing objects, that contribute to thermal gradients and radiation pressure forces. When 3I/Atlas passed through that pocket, when it flew through the region where Earth's influence is strongest, it entered a chain of influence. Sun to Earth to object. A cascade of forces and conditions that blurred the line between passive observation and active participation. The Sun heated 3I/Atlas, driving processes that might have been dormant in interstellar space. Earth's gravity deflected it, bending its trajectory in predictable ways but also possibly triggering tidal stresses that opened fractures or shifted internal layers. Earth's magnetosphere may have funneled solar wind particles toward the object or shielded it from particles that would otherwise have struck its surface, creating a complex particle environment different from what the object would have experienced in open space at the same distance from the Sun. The combination of influences, solar radiation plus Earth's gravity plus Earth's magnetic field plus whatever unique thermal or particle conditions exist in near-Earth space, created conditions that 3I/Atlas had never experienced before. Not in its journey through interstellar space. Not in its long fall toward the Sun. Not until it passed close to our world and entered the complex environment that exists nowhere else in the solar system except near other planets, and Earth's environment is unique among those. We did not reach out and touch this visitor. We did not intentionally change it. We did not even know it was going to deviate until after it happened, until the data came in and the residuals refused to disappear. But our presence mattered. Our planet's existence, our gravity, our magnetic field, our position in space, these altered the trajectory of something born under other stars, something that formed in a completely different stellar environment, something that has traveled farther than human civilization has existed. That is not power in any meaningful sense. We cannot control it. We cannot predict exactly what will happen the next time an interstellar object passes close to Earth. We cannot even explain precisely what happened this time. It is not control, but it is influence. It is participation. It is a reminder that gravity and magnetism and heat and the complex physics of plasma interactions do not ask permission before they act, do not care about boundaries or categories or human notions of what should and shouldn't happen. They simply operate according to their nature, shaping reality in ways that we observe after the fact and struggle to understand. What if this is normal? The question refuses to fade. What if every interstellar object that passes through a star system experiences these kinds of subtle changes? What if the universe is full of these interactions and we've simply never been able to detect them before because our instruments weren't sensitive enough, our models weren't precise enough, our observation networks weren't extensive enough? What if Oumuamua changed too, altered by its passage through the inner solar system in ways we noticed but misinterpreted? Its acceleration was detected, measured, quantified. The object moved slightly differently than gravity alone would predict. Scientists attributed it to outgassing, to cometary activity, even though no tail or coma was visible. But what if something else was happening? What if its passage close to the Sun and past Earth and other planets triggered internal changes that we couldn't fully characterize because we discovered the object too late, observed it for too short a time, lost track of it before we could gather enough data to understand what was really happening? What if Borisov was altered in ways we attributed to ordinary cometary activity without realizing that something deeper was occurring? Borisov looked like our comets. It had a tail and a coma, and it brightened as it approached the Sun, and its spectrum showed all the usual molecular emissions. So we classified it as an interstellar comet, added it to the catalog, and assumed we understood it. But what if beneath that familiar appearance, internal processes were occurring that had nothing to do with normal cometary sublimation? What if the environmental shock of entering our solar system triggered changes that happened to produce observable effects similar to cometary activity but that were actually something different, something we missed because the surface appearance matched our expectations closely enough that we didn't look deeper? What if the universe is full of these quiet interactions, subtle exchanges between interstellar visitors and the star systems they pass through, changes too small to be dramatic but real enough to affect trajectories and compositions and internal structures? What if we are only now, barely, finally, with our current generation of instruments and techniques and global observation networks, capable of detecting these effects? The thought is both humbling and exhilarating. Humbling because it suggests we have been blind. That for the entire history of astronomy, for centuries of watching the sky and tracking objects and building models, we've been missing an entire category of cosmic behavior. That interstellar objects have been passing through our solar system for billions of years, probably thousands of them, maybe tens of thousands, entering and leaving on timescales of decades, most of them too faint to detect with anything but our most modern telescopes, and we never noticed them reacting to their passage through our system because we didn't have the tools to measure the subtle deviations that mark those reactions. That our understanding of how star systems interact through the exchange of material has been incomplete, based on theoretical models rather than empirical observations because we lack the observational capability to test those models. Exhilarating because it means we are learning to see what was always there, hidden in the noise, invisible to earlier instruments but now finally becoming detectable. That we are witnessing a transition in our understanding similar to other moments in astronomical history when new instruments revealed phenomena that had always been there but that we couldn't perceive, when the first telescopes showed us Jupiter's moons and Saturn's rings, when photographic plates let us detect galaxies beyond the Milky Way, when radio telescopes opened a completely new window on the universe. We are learning to see interactions that have always been happening. We are developing the sensitivity to detect signals that have always been present. And with each new interstellar visitor, with each new data set, we are adding pieces to a puzzle that will eventually reveal how common these interactions are, how significantly they affect the objects that pass through star systems, what they tell us about the environments around other stars and how those environments differ from our own. 3i/Atlas forces us to confront an uncomfortable mirror. The metaphor is apt because mirrors show us not what we want to see but what is actually there, reflections that reveal truths we might prefer to ignore. Our solar system is not a sealed bubble, despite how we've imagined it in diagrams and textbooks. We draw the boundary at the heliopause, where the solar wind finally surrenders to the interstellar medium, and we imagine that boundary as a wall, a separation between inside and outside. But it's not a wall. It's a transition zone. The solar wind doesn't stop at a sharp boundary. It gradually weakens. The interstellar medium gradually strengthens. Objects pass through without noticing any discontinuity. And more importantly, influences pass through. Cosmic rays from supernovae light years away penetrate deep into the solar system. Interstellar gas and dust drift through the heliosphere. The sun's gravity reaches outward, technically extending to infinity though weakening with distance according to the inverse square law. Our planet is not an isolated stage, a theater where Earth's drama unfolds without connection to the wider universe. We exist within a dynamic exchange. Particles flowing past, solar wind outward, interstellar medium inward, cosmic rays from all directions. Fields intersecting, the sun's magnetic field carried outward by the solar wind, the interstellar magnetic field compressed where it meets the heliosphere, Earth's own magnetic field creating local distortions in both. Gravity reaching across vast distances, the sun's pull affecting comets in the Oort cloud more than a light year away, the galactic gravitational field affecting the sun's motion through space, nearby stars exerting subtle perturbations that accumulate over millions of years. Objects drifting through on journeys we will never fully comprehend, interstellar visitors like 3i/Atlas that pass through our neighborhood briefly, moving too fast to stay, carrying memories of other star systems and other planetary environments, altered by their passage in ways we're only beginning to measure. Every interstellar visitor that passes close to Earth becomes a probe, an unintended experiment, a test of our understanding that we didn't design and cannot control. They test the boundaries of our influence without ever intending to. They don't come to investigate us. They don't care about Earth or the Sun or anything else in our solar system. They're simply passing through on trajectories determined by gravitational interactions that occurred millions of years ago in regions of space we'll never observe. But as they pass, they interact. They feel our gravity. They enter our magnetic field. They absorb our thermal radiation. And in their reactions, subtle, strange, unexpected, sometimes barely detectable, we see reflections of ourselves. Not because they care about us. Not because there's any intention or awareness involved. But because we happen to be here. Because Earth happens to be massive enough to matter, close enough to touch passing objects with forces that travel at the speed of light and with gravitational fields that curve spacetime. Because our magnetic field happens to extend far enough to create a region where particle fluxes and field configurations are different from open space. We see ourselves reflected in the perturbations we cause, in the deviations we trigger, in the changes that mark the passage of an interstellar object through our neighborhood. And that reflection is uncomfortable because it reveals that we are not separate from the universe, not isolated, not protected by distance or emptiness from the consequences of our existence. We are part of it, embedded in it, connected to it through invisible threads of force and influence that reach farther than we imagined. As 3I/Atlas moves away from us now, as it continues its journey outward from the sun and back toward the interstellar medium it came from, the data has stabilized again. The deviations have stopped growing. The residuals remain in the historical record, permanently archived in databases, preserved in scientific papers, stored on hard drives around the world, but the object is no longer surprising us. It is leaving, following the hyperbolic trajectory that will carry it out past Neptune's orbit, past the Kuiper belt, past the heliopause, and eventually back into the space between stars where it will resume a journey that may last another billion years before it encounters another star system. It is leaving as all interstellar visitors must. It cannot stay. The sun's gravity is not strong enough to capture it. Its velocity is too high. Its trajectory too open. It came. It passed through. It deviated. It will leave. In a few years, it will be too faint for even our largest telescopes to detect. In a decade, it will cross the heliopause and officially exit the solar system. In a century, it will be light weeks away, far beyond any possibility of observation. It will vanish into the dark, becoming once again just another invisible object among the trillions that wander through the galaxy, indistinguishable from the background, lost to our instruments, reduced to a brief entry in catalogs and a collection of data sets that scientists will continue to analyze for decades, searching for clues we might have missed during the brief window when it was close enough to study. But the question remains. It hangs in the silence like a musical note that will not fade, like a vibration that continues long after the initial strike. Did it leave altered? Did something fundamental change inside that ancient body during the brief hours when Earth was closest, when our gravity was strongest, when our magnetosphere surrounded it, when our radiation environment was most intense? Did our planet's gravity reshape even one molecule? Did magnetic fields redirect even one charged particle? Did thermal gradients shift even one grain of ice? Did tidal stresses crack even one internal layer? We will never know for certain. The object is too far away now, moving too fast, too faint to study in detail. We cannot send a probe to catch it. Interstellar distances are too vast, closing velocities too high, our propulsion technology too limited. We will never be able to sample its surface or drill into its interior or measure its composition directly. All we have is the data we collected during those brief weeks when it was close enough to observe. The trajectory data showing deviations from prediction. The photometry showing subtle changes in brightness variation. The spectra showing no obvious signs of activity. And from that limited data set, we must infer. We must guess. We must build models and acknowledge their limitations. Perhaps it left unchanged in any fundamental sense. Perhaps the deviations we measured were temporary effects that have already faded, stresses that relaxed after the flyby ended, processes that activated briefly and then shut down again as the object moved away from Earth. Perhaps in a billion years, when it finally passes through another star system, it will show no trace of having visited us. Or perhaps it carries marks we cannot see. Perhaps internal fractures remain opened, weakening the structure in ways that will matter during the next close encounter with another planet around another star. Perhaps volatiles were redistributed, changing the composition of surface layers in ways that will affect how it responds to the next stellar radiation environment it experiences. Perhaps its rotation was permanently altered, tumbling differently now than it did before Earth, spinning in a way that will affect how forces couple to its motion during future encounters. And more unsettling, did we change? Not physically, Our planet's mass did not increase or decrease because 3I/Atlas passed by. Our orbit was not measurably altered. The gravitational effect of such a small body on Earth is negligible. No physical quantity that describes our planet changed in any way that matters. But in our understanding, something shifted. In our awareness of what is possible, of how the universe works, of how star systems interact through the objects that pass between them. We learned that proximity matters even in the vast emptiness of space. We discovered that interactions can be subtle, hidden in residuals and light curve irregularities rather than announced by dramatic visual changes. We recognized that nothing is truly isolated, that every encounter leaves a trace, that the universe is more connected and more reactive than we believed. That knowledge, that awareness, is a kind of change. It alters how we will observe future interstellar visitors. It shapes the questions we will ask, the measurements we will prioritize, the models we will build. It expands the space of possibilities we consider when faced with unexpected data. And perhaps most significantly, it deepens the mystery. Because now we know what we didn't know before, that something can change without announcing itself, that interactions can occur without obvious signatures, that the universe contains phenomena subtle enough to hide in plain sight, visible only to those who look carefully enough at the right quantities with sensitive enough instruments. And knowing that we don't know is more unsettling than simple ignorance ever was. The future watches us now with different eyes. This is not metaphor, not poetic language. It is literal truth. Every new interstellar object that enters our system, and we now know they come regularly, probably several passing through at any given time, most too faint to detect, will be measured more carefully than 3I/Atlas was. Because 3I/Atlas taught us what to look for. Modeled more precisely, with calculations that account not just for gravitational deflections but for possible interactions with planetary magnetospheres, with radiation environments, with particle fluxes that vary depending on solar activity and geometric configuration. Watched for subtle deviations that betray interaction, for trajectory residuals that persist across multiple observations, for changes in rotation or brightness that correlate with planetary flybys. We will look for timing. That is the key lesson from 3I/Atlas. Not just whether changes occur but when they occur. Whether deviations begin during close approaches to planets or only afterward, suggesting delayed responses. Whether rotation changes appear suddenly or gradually. Whether any observed activity correlates with specific environmental conditions. We will look for evidence of environmental shocks triggering dormant processes. Thermal pulses from solar radiation combined with planetary influences. Tidal stresses during flybys. Magnetic field interactions. Particle bombardment from concentrated solar wind. All the complex physics that occurs in the space near planets but that an object would never experience in open interstellar space or even in the outer solar system far from planetary influences. We will build better instruments. The next generation of telescopes, larger mirrors, more sensitive detectors, better pointing stability, global networks coordinated in real time, will be able to detect smaller deviations, fainter objects, subtler changes. We will refine our models, incorporating more physics, running higher resolution simulations, developing better theoretical frameworks for understanding how interstellar objects respond to stellar and planetary environments they've never encountered before. We will expand our definitions of normal, our taxonomy of behaviors, our classification schemes that currently divide objects into comets and asteroids and other categories that may not be appropriate for objects formed under completely different conditions. But we will never escape the central mystery that 3I/Atlas revealed. We will never be able to erase what we learned. We will carry forward into every future observation the uncomfortable knowledge that something happened. Not an explosion or collision or threat or disaster or moment of cosmic violence or dramatic event that changed the solar system in any measurable way. Just a deviation. Small. Persistent. Correlated with Earth's flyby in a way too precise to be coincidental. A response. That is the word that haunts those who study these things. Response implies interaction. It implies that the object was not just passively deflected by our planet's gravity but actively responded to our presence. That something about passing near Earth triggered changes that went beyond simple mechanical deflection. A quiet conversation between our planet and a visitor from beyond. Not a conversation of words or signals or intelligence. A conversation conducted in the language of gravity and heat and magnetic fields and all the other forces that shape reality at these scales. A conversation we observed without understanding all of what was being said, picking up fragments and residuals and hints but missing the full meaning because we can only see surfaces and trajectories, not internal states, not the full three-dimensional complexity of what occurs inside a body during environmental shock. And if something so distant, formed light years from here, traveling for millions or billions of years through space colder and darker than anything we can easily imagine, something so ancient that it predates our entire evolutionary lineage, that was already journeying through the galaxy when Earth's continents were still forming, when life on our planet consisted only of single cells, when the sun was younger and dimmer, something so fundamentally alien, composed of materials forged under a different star with different chemistry and different thermal history. If something like that can react to our presence, can change in measurable ways simply from passing near our world, then perhaps the most unsettling truth is not what changed in 3I/Atlas. Perhaps the real revelation, the discovery that will shape astronomy for decades to come, is what its change reveals about the nature of space itself, about the nature of interaction and influence, about how nothing is truly isolated in a universe connected by gravity and light and magnetic fields that reach across the void, about how space is not empty or silent or passive, not dead, but alive in a sense we're only beginning to comprehend, alive with invisible exchanges happening all around us in the dark. Interactions too subtle for our ancestors to detect but visible now to instruments sensitive enough to measure deviations smaller than a meter across distances of millions of kilometers. Alive with conversations between worlds that will never meet, between objects that pass in the night without collision but not without consequence. Alive with processes we are only now learning to observe, phenomena we are only now beginning to name, physics we are only now developing the mathematics to describe. The universe is speaking. It has always been speaking. Every trajectory carries information. Every deviation tells a story. Every interstellar visitor is a message, though not one written for us, not one we are guaranteed to understand. And we are finally barely learning to listen. Learning to hear the whispers in the mathematics. Learning to recognize the signatures of interaction hidden in data we once dismissed as noise. Learning to see what has always been there, waiting for us to become sensitive enough to notice. The future watches us because we are watching it, because every interstellar object that enters our system is a piece of the future arriving ahead of schedule, a sample of the galaxy delivered to our doorstep, an opportunity to learn what else is out there and how it behaves when exposed to environments like ours. And now that we know those objects can change, can react, can respond in ways that leave measurable traces, we watch them differently. With more care. With more instruments. With more questions. With the knowledge that every flyby is an experiment, every close approach a test, every trajectory a conversation we are privileged to observe if only we are patient enough and careful enough and wise enough to interpret what we see. The silence that follows 3I/Atlas as it retreats into the dark is not the silence of ending. It is the silence of anticipation.